All right, so we're going to look at quadratic functions. And we might remember that a quadratic equation is something of the form ax squared plus bx plus c, normally equal to 0, where a quadratic function is equal to f of x or y, same thing. And so if we think about what this graph looks like, well, this is x squared is the highest power term, so this is a parabola. So you're getting a picture that looks kind of like this, right? Possibly. And if we wanted to find out where the x-intercepts were, well, the way you find the x-intercept, you make y equals 0, or in this case, f of x equal to 0, and then you solve for x. Well, something that will solve this type of equation is the quadratic formula. So these x-intercepts are going to happen at those values that we get from the quadratic formula. So this one's going to be negative b, and I'm going to separate this 2a minus the square root of b squared minus 4ac over 2a comma 0. And this one's going to happen at negative b over 2a plus the square root of b squared minus 4ac over 2a comma 0. So I'm just separating those into separate fractions, and we'll see in a second why I'm doing that. Now, to find the y-intercept, again, the way we do that is we make all the x's 0, and we see what we get for f of x, or f of 0, I guess. And so if you make all the x's 0, f of 0, if it looks like this, would be c. Would be this constant value. And if you think about for a line what the y-intercept is, y equals mx plus b, it's the constant value as well. And that's actually true for all polynomials. As long as it's all multiplied out like this, this constant value will be the y-intercept. And then there's another spot that we want to find, and that is called the vertex. And the vertex is this point where it turns around. But we're going to use the fact that all parabolas are symmetric to a line that goes down the middle. So we've talked about some types of symmetry, but this is not one of the things we've talked about yet. But all parabolas have a symmetry to this vertical line. There's a line of symmetry, and it's halfway between any 2 points that are on the same height, including these x-intercepts. So if you think about this x-intercept is at negative b minus the square root of b squared minus 4ac all over 2a. And this one's at negative b over 2a plus the square root of b squared minus 4ac all over 2a. Then halfway in between those two would be negative b over 2a. You start at negative b over 2a, and then you subtract something off of it. You start at negative b over 2a, add something onto it. So the line, this vertical line here that we're symmetric to, is x equals negative b over 2a. So this vertex is on that vertical line. So the x value of the vertex is negative b over 2a. Should be an a. What's the y value? Well, just like with any kind of equation, if you're looking for what y or y values match up with an x, you plug that value into your equation and you work it out. So by definition, the y value would have to be f of negative b over 2a. Now, that's one way to write the equation, and that's how we find these various things. Another thing we've talked about is transformations. And so you can think of, what does y equals x squared look like? Well, that's centered at the origin, right? That looks ugly. Let's back that up. Let's try that again. I can do better than that. Getting a little diagonal here. Let's try it again. Yeah, there we go. That's a little bit better. All right, so this has been moved over some number of units and moved down some number of units, and we got the picture I drew over there, right? Well, we're going to call this new location, this vertex, hk. And if you think about these transformations, you're moving this h units to the right, so y equals some number of units to the right, and then you're moving down, but k, let's say k is a negative number, notice I put just a k here, so if we're in the negatives, it's negative numbers, so we're just going to say plus k. That covers the fact if k is positive or negative. And then, I don't know, maybe this is a little wider than it normally is, maybe it's a little skinnier, I don't know, all of that stuff is handled by a multiplier a. It should be noted that this a and this a are the same a. So another way of describing the vertex is calling it this hk. And you can write the equation in this format. So let's see where we're going to go with all this information. We're going to be asked to find the vertex and write the equation in the standard form. Okay, and the standard form is y equals a x minus h squared plus k, where the vertex is at hk. Usually we call it standard form something that is easy to draw the graph from once you have the equation. You can think about, this first format I wrote here is called the general form. Come on. This is called the general form here. And it's not really useful. I mean, you can find the y-intercept pretty easily, but other than that, it's not super easy to draw the graph without doing a bunch of mathematics. Whereas if it's in this standard form, you can move the vertex and then look at the a to tell you turn it upside down or something. So, we want to turn this into the standard form. So they're going to give us a function. They're going to say f of x equals 2x squared minus 3x plus 4. Okay? And they're going to ask us find the vertex and write it in the standard form. Now, there are some ways you can find the vertex and write it in the standard form at the same time, completing the square and stuff, and I'm not really going to go over that. I'm going to use the hk information. So, with the negative b over 2a. So, again, just like solving quadratic equations, a is what goes with x squared, b is what goes with x, c is what is a constant. So my b is negative 3, so this is negative 3 over 2 times 2. So 3/4 is the x coordinate of my vertex. So my vertex so far looks like 3/4 comma something. And what I need to do is figure out what that something is. And the way I'm going to do that is I'm going to plug this into the equation. So my k value is f of 3/4. So plug that in. 2 times 3/4 squared minus 3 times 3/4 plus 4. And I'm just going to have my calculator do that for me real quick. 2 parentheses 3 divided by 4 squared minus 3 times 3 divided by 4 plus 4, change to a fraction, 28 eighths, or 23 eighths. 23 eighths. And so, now that I know what the vertex is, this is again hk, and I know what my a is, I can write this equation. I can say, oh, in the standard form, f of x equals, again, it's the same a number, so 2 parentheses x minus h, so minus 3/4 quantity squared, and then plus k. K we found was 23 over 8. And so there it is in the standard form. So that's how you turn something in the general form into the standard form, and you can find the vertex at the same time. So let's look at a more general type of problem. Let's say we were asked find the intercepts and the vertex. Okay, and so we have g of x equals, let's make it a little interesting, x minus 1 squared, 2 times x minus 1 squared minus 8. Okay, so actually the easiest thing here to find is the vertex. Why? Because this is in the standard form. And so I can look at here, remember this is y equals a x minus h squared plus k. So h must be 1. Notice this is an x minus, so h must be 1. An easiest way is just think about what makes this part 0, positive 1. And then plus k, so k is exactly what this number is. This number is negative 8. So 1, negative 8, that's the vertex. Let's say we want to find the y-intercept. Well, it is not negative 8 because this is not in the general form. Now you could distribute all this out and put it in the general form, but it might be easier just to say, you know, what is g of 0? What do you get when you put 0 in there for x? So let's just work that out. So this is a negative 1 squared is 1 times 2. So this is 2 minus 8, which is negative 6. So the y-intercept is at 0, negative 6. And then we get to the x-intercept. And you know, usually the x-intercepts are the hardest ones, assuming they even have x-intercepts. If you get an imaginary number or something, we're going to say it doesn't have an x-intercept. But this one I set up to have x-intercept. So let's say 0 equals 2x minus 1 squared minus 8. Again, it's just like finding the zeros of a function. You make the y or the f of x or g of x in this case equal to 0, and you solve for x. So I'm going to add 8. I'm going to get rid of that 2 there. I'm going to divide by 2. That'll give me 4 equals x minus 1 squared. And I want to get rid of this square, so I'm going to square root both sides of the equation, and that's going to give me plus or minus 2 equals x minus 1, and then I'm going to add 1. And I usually, when I do that plus or minus, I put the number in front of the plus or minus in order to figure those out. So it's going to be positive 3 and negative 1. So I have x-intercepts at 3, 0, and negative 1, 0. Now let's say I wanted to graph this using this information. So let's see, we got to go down to negative 8. 1, 2, 3, 4, 5, 6, 7, 8, negative 8. You gotta go over 3, there's an x-intercept. You gotta go to negative 1, there's an x-intercept. Y is at negative 6. We're told the vertex is at 1, negative 8. I actually do know another vertex here, or another point, and that point is at 2, negative 6. Now the reason why I know that is because, again, parabolas are always symmetric. So since I know, you know, this is over 1 and up 2, this one's got to be over 1 and up 2. And then I'm just going to kind of, you know, let's see how well I can draw this parabola. Not very well, but okay, something like that. So, but that's how you find those different aspects of the function. Okay, let's see another thing we're going to look at. So I kind of mentioned this. You might be asked to find the zeros and the x-intercepts. So this is a good time to talk about some relationships between these. And we've already mentioned this before, but let's say we have f of x equals x squared minus 7x plus 10. Okay, and so to find the zeros, I set this equal to 0, and I solve it. And again, I could use a quadratic formula or anything, but this is factorable, so I'm going to go ahead and factor this as x minus 5, x minus 2, factors of 10 that add and make 7. Both of them are negative. So these are the factors. Okay, I set each one of these equal to 0. I work that out. Add 5, add 2, and I get x equals 5 and positive 2. And these are the zeros. And then if I write these as coordinates here where the y values are 0, these are the x-intercepts. So if I say give me an x-intercept and you say 5 and 2, you're actually giving me the zeros. You're not giving me the x-intercepts. They're very closely related. In fact, if you could look at the graph of this and you saw that it's hit at 5, 0, and 2, 0, you would know the zeros were 5 and 2. And then there's the factors, and the factors are also related to those. So these three factors, zeros, and x-intercepts are all related to each other. They're all different ways of representing the same kind of information, but they're not the same. So, if I ask for, x-intercepts, don't give me zeros. If I ask for zeros, don't give me x-intercepts. But they are all connected to each other. Let's say we wanted to find the quadratic equation, or let's say function, quadratic function with vertex at -3, 5, and going through the point I don't know, 6, 1. Okay, so we want to find that quadratic equation. Now, there were two types of ways of writing a quadratic equation. There was the general form, and there was the standard form. And theoretically, if you're looking for an equation, you could use either one. The problem there is you have to look at how much information you know. And in this case, we only know 2 points, and one of those is the vertex. So since I know the vertex, I probably want to use this standard form, which has the vertex directly in it. So I'm not going to use this general form. Later on in the semester, we will look at problems doing this, but what we'll see is you actually need 3 points in order to do it, not 2 points. So since I know the vertex, I can fill that into my formula. It's y equals a x minus -3 squared plus 5. And again, this is really just x plus 3. And then I need to figure out what this a is, and that's where this other point comes in. So this says when x is 6, y is 1. Now x isn't always going to be 6, and y isn't always going to be 1. But if x is 6, y is 1. Well, we can use that fact to figure out what this multiplier has to be. So if we fill in 1 for y and 6 for x, we can figure out what a has to be. So I want to figure out what a is. What's this? It's 9. Let's try to get a by itself. So I'm going to get rid of that 5. So -4 equals, we said this is 9 squared is 81. So this is 81a. Divide both sides by 81. And you get a is -4 over 81. Now don't stop there. Remember, we're looking to plug this in to the equation. So this is going to be y equals -4 over 81, x plus 3 squared plus 5. You can say f of x if you don't want to use y. Again, it's not that big a deal, which notation you're using in this case when it's just asking you to create a function on your own. If it really bothers you, you can always say y of x, and there it is, function notation. Okay, so that's something we're going to do. Let's look at this. Let's say we wanted to find a quadratic equation or function with x-intercepts of, let's say the x-intercepts are 2/3, 0, and -5, 0. Okay? Well, what we're going to do is basically what we did earlier on this problem, where we looked at find the zeros and find the x-intercepts, and we factored and found the zeros, and we found the x-intercepts. What we're going to do is this process backwards. We're going to work our way back up to the function or the equation. So I have the x-intercepts. What that tells me is my zeros are x equals 2/3 and x equals -5. Well, if those are my zeros, I can use those to find out what the factors are by getting each of these statements equal to 0. So x minus 2/3 equals 0, add 5, and x plus 5 equals 0. Now, I could use these, but this would involve foiling out in a statement involving fractions. I don't know about you, I don't really like fractions. So I'm going to go ahead and multiply this one on both sides of the equation by 3 by the denominator, and that'll get rid of that fraction. It'll be minus 2 equals 0. And, 2/3 still makes that 0, but it's going to be easier to work with. So my function is going to have factors 3x minus 2 and x plus 5. Again, these are the factors that I found. And then I'm just going to distribute this out. So 3x squared plus 15x minus 2x minus 10. So my function could be 3x squared plus 13x minus 10. Now, the problem here is, well, it's not a problem. I mean, this is an answer. But there is a little distinction between this and the previous one. There's big differences. Here we knew the vertex and a random point. Here we knew x-intercepts. So those are big differences. But there's a subtle difference here. That subtle difference is this is find the quadratic function or equation. This is the only answer. I mean, you can rewrite it in different formats, but that is the answer. On the other hand, this says find a quadratic equation, not the quadratic equation. And there's a distinction there. This is with only the x-intercepts, I can find kind of a format for those answers. But, let me give you another possible answer. This would also be a correct answer. Let's say -6x squared, -26x plus 20. How did I get that? Well, I multiplied everything in here by -2. And that's how I got that. And basically, this function kind of does this, and this function, is steeper and it's upside down. But the x-intercepts for these are the same. They have the same x-intercepts. Everybody else moved around. In fact, the most basic format of this type of possible answer would have looked like x squared plus 13/3 x minus 10/3. That's what we would have gotten if we had stuck with this x minus 2/3 version. So we've already changed what this answer could look like based on the x-intercepts, or based on having fractions or not. We multiplied both sides. So we changed this factor. We said it's still, 2/3 still makes it 0, and 2/3 does. 2/3 makes this g of x 0. But this is without multiplying everything by 3. So this is kind of like the most fundamental version. This is, a slightly more useful version, and then this, just a random version. So there's lots of possibilities of these that have these x-intercepts. In order to find which function you really wanted, you would need a third point to find some kind of multiplier you're using for everything. All right. Last thing, let's look at using quadratics to solve maximum and minimum problems. Okay, so let's say you have a parabola facing upwards. It's going like this. And say we have another parabola that's facing downwards. Well, the one that's facing upwards has some lowest spot. and we're going to call that lowest spot the minimum. And then the one facing up has some highest spot, we're going to call that the maximum. In both of those cases, a name that can describe that location is the vertex. So what we're really talking about is the vertex. And if you remember the vertex, that was negative b over 2a, and then you plug that back into your equation to figure out what the y value is. And usually when we're talking about maximum minimum, we're talking about the maximum minimum y value that the graph reaches. So this is if you have the x squared term is positive, this is if the x squared is negative. And so we can use that idea here to solve some problems. So let's say we had something like this. We had some kind of fencing that was subdivided. So this is x, this is x, this is x, and we got a y up here and a y down there. Okay, and so we're making some kind of fenced area here. And we're told all the fencing counted to 300 feet of fencing. That's what we used. And we want to know, we want to maximize the area. Okay? So what we're going to do is start off by writing an equation based on the amount of fencing we're using. So we have 3 x's and we have 2 y's, and that should all come out to be 300 feet. Okay? Then we're told something about we want to maximize the area, so we have to think about how would you calculate the area of this. And we're just going to assume these fences aren't significant in the area. So this is going to be, just basically one big rectangle here. So the area is length times width, or x times y here. And we're going to combine these two equations. And probably the easiest way to do that is to solve this 3x plus 2y equals 300 for one of the letters. So let's solve it for y. You could solve it for x also, but I'd rather work in halves than thirds. So negative 3x plus 300, divide everybody by 2. And so y equals, I'm just going to make that negative 1.5 x plus 150. So this is saying this length value is 150 and then minus 1.5 x's. So I'm going to put that in place of the y in my area formula. So area equals x times what we just said y was, negative 1.5 x plus 150. And so if I just distribute that, negative 1.5 x squared plus 150x. Well, this is a quadratic equation for the area, and it's going facing down. So I have this situation. I have a maximum situation. I want to maximize the area. So I want to know what should x and y be in order to maximize that area. Well, to figure out what x gives me the maximum area, I can look at the vertex. In this case, h is going to be the value of x that maximizes that area. So, negative b, so negative b, negative 150 over 2 times negative 1.5. So that's really negative 3. It's going to give me 50. So this side is 50, this side is 50, this side is 50. 50 feet, 50 feet, 50 feet. So then the question is, well, what's these other sides? And what I can do is I can take that and plug it into my formula for y. And say, well, let's take negative 1.5 times 50 and add that to 150. So what's that? It's going to be negative 75 plus 150. So 75 feet. So this side's 75 feet, and this side's 75 feet. So what dimensions would give us the maximum area? 50 feet by 75 feet. That would be the maximum area. Now, if I wanted to know what the maximum area is, what I could do is I could plug this in to my area formula. Or I could just multiply these two together as well, and that would tell me what the maximum area is what is. But a lot of times what they want to do is, what are the dimensions that will give you that maximum area? So that's a way you can use that formula create a quadratic formula, and then you can use the vertex to maximize it, because again, where that maximum occurs will be the vertex.